All right, good morning, guys. Happy Friday. I'm going to try to finish section 5.4 today. These are the day 5 notes. I don't know. I'll have to see how we feel towards the end, if we've gotten through enough equations to feel confident or not. But next week, I am not here next week on Wednesday, Thursday. So I'm most likely just going to try and finish up this section, and then next week will just be you guys working on a study plan, and then your quiz will probably be Friday. At some point you'll have to get the quiz done, okay? So next week will just be, you guys reviewing while I'm gone. I don't want to leave you guys videos and stuff like that to start the next section. Just review this, take the quiz, and we'll start it back up when I get back, okay? All right, here we go. So this is day 5. This is all about solving logarithmic or exponential equations, basically. So this is where you kind of start using a log and an exponential function to undo one another. And it's like we would use a square or a square root to undo one another when we're solving an equation, okay? All right, well, first let's go back to how we truly prove inverses, how we prove that one function is really undoing another function, and it's proving that their compositions both cancel each other out and leave you with x. So let's look at an exponential function, f of x equals 2 to the x, and g of x equals log base 2 to the x. So you have a base 2 exponential function, and then you have a base 2 logarithmic function. Oh no, guys, your cameras just went black and started blinking. Can you hear me? Am I clear? You guys look like you froze.
Yes, we can hear you.
I'm okay? I'm not going in and out?
Not at all.
Okay, good, because it's just my end then. All right, because you guys are going really wonky all of a sudden. All right, perfect. All right, here we go. So let's prove this. So we have a base 2 exponential and a base 2 logarithm. So let's prove first that f of g of x, when I plug the g of x function into the function f, that all operations cancel each other out. So that would be f of g of x is log base 2 of x. So I'm plugging log base 2 of x into function f, which would look like this. Function f is 2 to the x comes out, and log base 2 of x goes in its place. So you have a base 2 exponential being raised to a log base 2 of x. So guys, if you forget that this is a function for a second, just think of this problem. If you had 2 to some power, right? Granted, this is a really weird looking exponent, but if you had 2 to some power, that should equal an answer. You should get an answer to that. When you take a base 2 and you raise it to a power, you should get an answer. So guys, right now this equation is written in exponential form. Let's convert it to what his log form would say. A log would say log base 2, right, because we have a base 2 exponential, of, who do you take the log of? You take the log of the answer, and then who does a log always equal? The exponent, and this was your exponent. So guys, if log base 2 of this equals log base 2 of that, what does this and that have to be to each other? What does the missing answer to this function have to be? It has to be x. So in reality, this is what I'm talking about. It's hard to see the undoing happening, but it's happening. You're left with just x when you take a base 2 exponential and you raise it to a log base 2 of x. Because guys, what's actually happening is this base 2 exponential and this log base 2, they're canceling out and they're leaving you with just x. All right, now let's prove the other composition. Let's prove that g of f of x, all operations cancel out and also leaves you with just x. All right, so this is going to be g of f of x was 2 to the x. So I'm plugging 2 to the x into function g. So if I do that, it's going to look like log base 2 of x comes out and 2 to the x goes in, right? So you're taking a log base 2 of a base 2 exponential. So again, forget this part for a second. Just think about this logarithm right here. Log base 2 of 2 to the x, guys. There should be an answer to that logarithm. There should be an answer to this problem. So since it's written as a log right now, use your log loop and convert this back to exponential form. What does the equivalent exponential form say about this logarithm? It's saying that 2 to that power has to equal that answer. 2 to that exponent has to equal that answer. Well, guys, what does this missing answer have to be in order for 2 to that to equal 2 to the x? This has to equal x. So yet again, all operations are canceling each other out and leaving you with just x. So when you take the log base 2 of a base 2 exponential, they are really canceling each other out and leaving you with that x value. Okay, so that's how we're going to be able to use these exponential and these logarithms to solve equations. If I have to solve an exponential, I can use a log to undo it. If I have to solve a logarithm, I can use an exponential to undo that equation. All right, so the formula says that if you have a base a exponential raised to a log base a, those two functions are going to cancel each other out and leave you with just x, whatever you were taking that log of. And the reverse works as well. If I have a log base a of a base a exponential, that log and that exponential are going to cancel each other out and leave you with just x. Okay? All right, so look at here. If they ask you to find what's 4 raised to the power of log base 4 of 16, guys, think about this. What does a base 4 exponential raised to a log base 4 do? It cancels, and it leaves you with 16. So we're going to be able to use this to undo things. All right? A base 6 exponential raised to a log base 6, they're going to cancel each other out and leave you with just x. Okay? Look at this one. A log base 3 of a base 3 exponential raised to a power of 81. What is the log base 3 and the base 3 exponential going to do to each other? They're going to cancel, and it leaves you with 81. Okay? All right, look here. I have a base e exponential raised to a natural log. Now remember, who is the assumed base of a natural logarithm? It's base e. So if you need to see that, the base of that natural logarithm is e. So a base e exponential raised to a natural log base e, they're going to cancel and leave you with just 5. And then last, if I have the natural log, which is assumed to be base e, of a base e exponential, they're going to cancel and leave you with that x value. Is everybody okay? Everybody good? Okay. So we're going to use that to solve our equations. Now, I just want to remind you guys, when you start solving equations and you're involving exponentials and logarithms, there's a couple things I want you to remember. Remember, the base of an exponential, by definition, was never allowed to be a negative number. Therefore, it was always positive. So a positive base raised to any exponent always made a positive number come out. So only positive numbers came out of an exponential, right? Not 0, not negative numbers, which means when those outputs became the inputs to our logs, we were not allowed to take the log of a negative number or 0 because they did not come out of an exponential. So just remember that, because you may get an extraneous solution when you're solving a log equation. You might be getting a number because you did all the math correctly, but it just doesn't make sense to be an answer to that problem, because maybe that answer means you'll be taking the log of a negative number or 0. So you always want to check your answers when you solve a log equation for extraneous ones, because we are not allowed to take the log of a negative number, and we are not allowed to take the log of 0. All right, ready? Let's do this. Let's solve some logarithmic equations. So guys, in this section, they keep the logarithm equations extremely basic, just kind of getting you guys used to what we're going to be doing, just kind of let you guys see the ropes, all right? In section 6, I believe, we'll see some more difficult log equations. So I'm going to try to train you now how to approach those more difficult ones, okay? So there's 2 ways to solve the equations right now. I'll show you both ways, but there's really one way that I want you to get used to doing. All right. So guys, the first thing you'd want to do when you solve a log equation, right? I have to find out what x value makes the log base 3 of this number equal to. The first thing you want to do is isolate the logarithm. I have. This is log base 3 of that equals 2. There's nothing on the left side of the equation attached to this log that I would like to move away. So isolate the log, that's already done. So one thing you could do is, right now, I am not getting anywhere in log form. So you could use your log loop to rewrite this in exponential form. So what would your log loop say about this? It would say 3 squared equals that answer, right? Our log loop would say 3 to that power equals that answer. And now my x value is broken out of that logarithm and I can solve for it. So I would get 9 equals 4x minus 7. I'll add over my 7. I'll get 16 equals 4x. I'll divide both sides by 4 and I'll get x is 4. And now this is what I mean. Just make sure that if x is 4, is 4 times 4 minus 7 going to turn into you taking the log of a negative number or 0? No, because 4 times 4 minus 7 is not 0, is not a negative number. So always check for that. All right, so that's kind of how your book is going to show you how to approach these equations right now, just because they are pretty basic. So if you were to use the question help on your homework, that's probably what you would see. I want you guys to get used to doing this. When we get to these more difficult log equations in section 6, I want you to remember who's really going to undo that log equation. It's the exponential form of the equation, right? So this might seem a little weird to you guys, but if I have right now a base 3 logarithm, and sorry, I looked at the wrong camera. I thought my hand wasn't on camera. If I have a base 3 logarithm and I need to undo it, who should undo a base 3 log? A base 3 exponential. So what you can do is you could exponentiate both sides. You're going to, what I say, base both sides of the equation to a base of 3. Just like you would square root both sides to unsquare something, you can base or exponentiate, I think is what your book would call it, but I don't like it. It's too fancy for me. I would base both sides of the equation to a base of 3. So what is a base 3 exponential due to a base 3 log? Cancel. I'm left with 4x minus 7. And then it equals base this, right? This is now a base of 3 and an exponent of 2. 3 squared. And you end up getting the exact same equation to solve. So that's what I would like to train you for. If we're going to undo a log, let's base both sides of the equation. Right now, with being them basic, you could get away with just rewriting it in its equivalent exponential form. But I want you guys to get used to this basing both sides of an equation, okay? Because if you ever had to solve a log inequality in the future, there's no guarantee with a log inequality that when you do the log loop, that the symbol is facing the correct direction. So you would base both sides of an inequality to make sure the symbol stays in the right direction. So I want you guys to get used to this function or this, I would say, tool. All right, here we go. So let's solve this one. Log base x of 64 has to equal 2. So now the unknown value isn't what we're taking the log of, it's the base of the actual logarithm itself. It's fine. So guys, what I would tell you to do is, if this is, I'd isolate the log, but it is. I would undo a log base x by basing both sides of the equation to a base of x. All right, so now what is a base x exponential due to a log base x? They cancel. I'm left with 64 equals base x to a power of 2 now equals x squared. And now I'm left solving this equation for x. So let's square root both sides, and x ends up equaling positive or negative 8. But let's double check. If x was positive 8, could the base of our exponential function, of our logarithmic function be base 8? Yeah, right? An exponential could have had a base of 8, so our log could have a base of 8. However, if x was allowed to be negative 8, that means the base of your logarithmic would have been negative 8. Would your exponential function ever allow you to have a negative base, and therefore now you'd have a negative base of a logarithm? No. So negative 8 is extraneous, only positive 8 is kept as the answer. So you have to make sure that you don't keep any extraneous solutions. Okay, and then guys, just for giggles, because we are on these basic equations, if you used your log loop, if you converted this to exponential form, it would have said x to that power equals that answer, and it would have left you with the exact same equation to solve if you hadn't based both sides. I just want you guys to get used to that function. All right, here we go. Look at number 5. If we have to solve this log equation, well, the first thing you need to do is isolate the log. That's 6 and that negative sign, they can't be on the same side. You got to get the log by itself before you could base both sides or use your log loop. So let's get the log by itself. So let's minus 6 the opposite of the log of x equals -3. Divide by that -1 in front to get rid of it. And now you have the log of x equaling 3. Well, guys, who is the base of a log assumed to be when nothing is written there? This is your common log, right? The base is assumed to be 10. So if you need to see it, write that in there. That's a base 10 log. All right, so who's going to undo a base 10 logarithm? A base 10 exponential. So let's base both sides to a base of 10 and get rid of it. So a base 10 exponential and a log base 10 cancel. I'm left with just x. And x will equal base 10 to a power of 3 is 10 to the third, which is 1,000. So now just make sure if x is 1,000, I'd be taking the log of 1,000, which is perfectly okay. It's not making me take the log of a negative number or 0. So that's a perfectly acceptable answer. All right, and again, because these are simple, your log loop would have ended up with the exact same equation. 10 to the power of 3 equals that answer x. I just want you to get used to the basing. All right, let's try a natural log. Let's look here. So if you said you had the equation, the natural log of x needed to equal 2, right? Well, first you'd isolate the log, but the log is already by itself. Now who is the base assumed to be in a natural logarithm? E, right? So who would undo a base E logarithm? A base E exponential. So let's base both sides to a base of E. They cancel. It leaves me with just x. And then my answer is going to be a base E to a power of 2, which is E squared. And we tend to leave the E's, the answer, in terms of E, because that's the most exact answer. Remember, E is a really long irrational decimal, so we don't want to square it and get the answer because it's really, really ugly. It's like 7.3, blah, 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 blah. Really long, never ends, never repeats. So your most exact answer is E squared. And since E squared is a positive number and not 0, it's not an extraneous solution because that means I would not be taking the log of a negative number or 0. Okay, let me pause before your cameras start blinking on me again. Can I get a thumbs up that we're okay? Am I making sense? Are we good? All right. So again, technically right now, all of these equations have two ways to solve them. You can base both sides or you can use your log loop. Like I said, your book right now is going to show you your log loop, converting this to exponential form. I want you to get used to basing both sides though. All right, let's go to my next page. Let's see what we got. All right, if I'm going to solve this log equation, right? First, I got to isolate the log. So I'm taking log base 6 of 4x. I got to get that by itself. So that's 7, that 5, they got to go. So just like solving equations, let's move the one that's not attached first. So minus 5, I'll get 7 times log base 6 of 4x equals negative 7. Let's divide that 7 away. Now I get log base 6 of 4x equals negative 1. All right, so now, like I said, two options. Log loop your way out, 6 to that power equals that answer by converting it to exponential form, or who's going to undo a base 6 log? A base 6 exponential. So let's base both sides to a base of 6. So they cancel each other out. I'm left with 4x. Guys, you're left with 6 to the power of negative 1. 6 to the power of negative 1 is 1 over 6. So I'm going to put 1 over 6. All right, I'm going to cross multiply. 4x times 6 is 24x. It equals 1 times 1, which is 1. Divide by 24, and x has to be 1/24th in order to make this true. Now again, just double check. If I plug 1/24th in, 4 times 1 over 24, guys, is that a negative number or 0? No. So you're perfectly fine and it's not extraneous. Okay. Two ways to do the next one. Right away, I want you guys to get used to seeing the log of something that you know. So right now, do I expect you guys to know what log base 6 of 4x is? No, nobody does right now. But if you were to see log base 6 of 36, think about what that's asking you. Log base 6 of 36 is literally asking you 6 to what power is 36? Everybody should know the answer to that logarithm right now. 6 to what power is 36? It's 2. So you should try to get used to seeing logs that you know so you can answer them and get them out of the equation. literally that's 2. So your equation is saying 2 has to equal 5x plus 3. And now it's not even a log anymore to solve. Just solve this teeny tiny linear equation, right? So I'm going to minus 3, get negative 1, divide by 5, and negative 1/5 is x. And it's definitely okay because I'm not even plugging negative 1/5 into what I'm taking the log of. I'm plugging negative 1/5 in right there, and that's perfectly fine. That couldn't be extraneous. All right, let's say you missed it. Let's say you're like, damn it, I didn't see it, Hardy. I didn't know log base 6 of 36 was just 2, right? It's okay. You'd be okay if you kept doing what I showed you. Okay, let's say you're like, all right, you're just going through the motions. I'll base 6 to both sides. They cancel. I get 36 equals 6 to the 5x plus 3. Well, now you could be sitting scratching your head saying, like, what the hell did I just do? How am I going to solve for x now, right? Well, guys, it turns into one of those equations where if you're solving for x, normally, and he's in your exponent, normally you need a log to solve for that because the unknown is part of your exponent. You need to get it out of your exponent, which a log will do. But it's one of those ones where you can rewrite 36 in the same base as this one, and then it's going to end up saying 36 is 6 squared equals 6 to the 5x plus 3. And now it's if 6 to that equals 6 to this, what do the exponents have to be to one another? They have to be equal. And you end up setting your exponents equal to one another. All right, and you get the same exact answer. So even if you didn't recognize that you know the answer to log base 6 of 36, you could still go through the motions and solve the equation by basing both sides. All right, how are we doing, guys? Are we all right? Yes? Okay. All right, so guys, those are log equations that we use exponentials to solve with. Now we're going to do the reverse. Let's look at an exponential equation that we need a log to solve. So before we were basing or exponentiating both sides, now we're going to have to log both sides. I'm going to try and get some of these done before the bell cuts me off. All right, well, guys, I was going to start with this one, but this one is just like this. It's one of the ones where you could rewrite 27 as 3 to the third and set your exponents equal. It's one of those equations that you don't need a log in order to answer and find out what that missing x value is up in your exponent. So let me just jump right to this one. Let's say they asked you 10 to what power is 75. Well, guys, we know 10 to the first is 10, and we know 10 squared is 100. So 10 to what power is going to get you 75? 75 is in between 10 and 100. So it's literally some decimal between 1 and 2 that you have to raise 10 to in order to get 75 as your answer. We don't know, though. We could sit here all day plugging and chugging decimals in between 1 and 2 until we get to the closest number to 75. There's an easier way to do this. If you don't know 10 to what power is that, who's going to undo a base 10 exponential? A log base 10. So we're going to log both sides of the equation. So now a base 10 log and a base 10 exponential cancel, and x is equal to whatever the log of 75 is. You have to take the log of 75 to figure out this answer. And the reason we write it like that is because that's the most exact answer we could put. Now it becomes a calculator problem to find out the actual estimated answer. So I don't know if you guys can see this, but on your calculator, everybody should have log buttons over here. So normally calculators only let you do base 10 logs or base E logs on the calculator. That's all they were programmed to do. They didn't do base 2 logs, they didn't do base 3, they didn't do base 7s, they just did base 10 or base E. But now the graphing calculators will do any base. So guys, if you hit log, what did we say, 75, hit enter, it's about 1.87506,123. That's the power you got to raise 10 to in order to get 75 as your answer. But we don't want these ugly decimals. So the most exact answer you can give is just the log of 75. So sometimes when you're solving an exponential, the log is part of your answer now. All right. All right, what about the next one? E to the x equals 7. Well, first, you would isolate the exponential. It's already alone. E to what power is 7? I got no idea, right? Who's going to undo a base E log? a natural log, a base E log. So we're going to natural log both sides of this equation. So the natural log and the base E exponential cancel. It leaves you with x. And your answer is going to be whatever the natural log of 7 is. And you can just ask your calculator for that estimated answer. So you have a natural log button over here too. So the natural log of, what did we say, 7? It's about 1.945910149. That's the power you got to raise e to get an answer of 7. But like I said, if we estimated that, it really wouldn't make the equation exactly true. So we want the exact answer, which is the natural log of 7. Okay? All right, look at number 12. First things first. If we're going to undo the exponential, first you have to isolate the exponential. So right now, e is being raised to the power of 3x. 2 is not. So 2's got to go away. He's got nothing to do with what's being raised to this power. So divide both sides by 2. You get e to the power of 3x equals 3. Now, who's going to undo that base e exponential, a base e log? So natural log both sides of this equation. All right, the natural log and e cancel. 3x is left equaling the natural log of 3, which, guys, it's just a very ugly decimal that we don't want to have to write down. So leave the natural log of 3 as part of your exact answer. And now all you have to do to get x by itself is divide both sides by 3. So x ends up equaling whatever the natural log of 3 divided by 3 is. And it's just an ugly decimal. The natural log of 3, enter, divide that by 3, and it's about 0.36620400962. It's just ugly. These are ugly answers.
How come you don't write the natural log of 1 as your answer for x?
Where would I be writing the natural log of 1 when we go back? Here?
Yeah.
Well, I'm not taking the natural log of 1. I had to take the natural log of 3 on this side.
Yeah, but like when you have the 3x equals the natural log of 3, and you're dividing by 3 on each side, wouldn't the division...
Oh, no, Michael. This 3 is inside that logarithm. You can't get to him. It's who you're taking the log of. It's almost, you can't get to that 3. I'm sorry. He's in the logarithm. He's what you're taking the log of. This 3 doesn't have access to him. Does that make sense?
Yeah.
Okay. It's kind of like if you had like the square root of, I don't know, like 10 divided by 2. You can't get to that 10 because he's under the square root. You can't divide that 10 by 2, right? Okay. All right. Oh, the bell's there. Let me see if I can do one more. So if I do the e to the 5x minus 1, right? You have a base e exponential, and it's isolated. We can natural log both sides to undo that. They cancel. I'm left with 5x minus 1 equals the natural log of, and I'll do this, of 9. He's inside that log. You ain't getting to him. All right? Now we got to solve for x. Add 1. You're going to get 5x equals the natural log of 9. That's separate. And then you'd add 1 to like the outside of that. And then you divide it all by 5. So this answer is really not pretty. It's x equals the natural log of 9. Then you add 1. And then you divide by 5. So because we need to keep our answers exact, these answers to this way, when you're taking the log of both sides, they're not pretty. All right, I'm going to let you guys go. Thank you so much for letting me finish that. I'm going to fill these two in on your filled in notes. So if you need to see them, they just have some setup. You got a minus 1. You got to divide by 4. You got to isolate your exponential. Here you got to add 2, divide by 3, isolate that exponential before you logging both sides. Okay. Are you guys okay? Can I get a thumbs up? Everybody okay? Again, these are pretty basic log and exponential equations right now. So we'll see some, more nitty gritty ones in section 6. Okay. You do have a homework, guys. I didn't make this homework due until Tuesday night because after this homework, it's really just reviewing and doing the study plan until the quiz on Friday. So I tried to give you guys plenty of time to finish up any of these homeworks. I'm going to try and get the study plan up this weekend, and that way it'll be available for the weekend and even next week. Okay. All right. I'm just have to double check the attendance real quick.